Okay, good afternoon, everyone. Welcome again. So today we have another graduate of ours as speaker, thanks to the benefits of the pandemic. Emre is currently a PhD candidate at ETH Zurich, working in the Advanced Interactive Technologies Lab, supervised by Professor Otmar Hiliges. His research interests lie at the intersection of machine learning, computer vision, and human-computer interaction, focusing mainly on perception and synthesis of human activities. He received both his bachelor's and master's degrees from our department in computer engineering. And prior to joining ETH, during his time with us, he worked with Fatih Hoca on pattern analysis of fMRI data. And now he's going to talk about the recent Generative paper and CVPR paper. It's nice to have you with us, Emre, and the screen is yours.
Thank you. Thank you. It's really great to be back, and thanks for having me today. I'm as a former ImageLab member, I'm really happy to give you this talk today. So let's start. Today I'll talk about our recent works and how we leveraged compositional and structural task priors in our models. So in the first part of my talk, I'll present you our recent paper, Compositional Stroke Embeddings, where we propose a novel generative model for digital ink data. And in the second part, I'll switch to a completely different problem domain, namely 3D human motion, and I'll explain you how we do representation learning for motion prediction by using the human skeletal configuration. So let's continue with the first one. So digital ink data appears in various types, such as handwritten text, sketches, doodles, or like hand-drawn flowcharts. It's still not as common as the traditional pen and paper, but like the devices are getting better and digital ink and the applications are gaining popularity. So this motivates us to develop new models for the digital ink data, specifically tailored for this data to provide users a better experience and compelling applications. So we are interested in modeling the data in time series representation rather than images, because time series representation is directly the sensory information we get from the devices. And when we model the time series representation, this allows us to interface our models with applications directly. So let's take a closer look to the data. In the time series representation, the data is just a sequence of 2D positions on the device screen. So here you see an image of a text generative modeling. And if you look at how the letters are constructed, so we basically render the sequences of points. Let me highlight you here. And like those points are basically 2D screen coordinates, X and Y. And we additionally have a label P, which corresponds to the pen up event label. So it takes the value of 1 when we lift the pen up, otherwise it's 0. So this point-wise representation has been the representation used in all the previous work. So if we take a closer look to the previous work, we see examples of handwritten text where like handwritten text is represented as a sequence of points, and this data is passed to RNN-based architectures for the task of like synthesis, editing, or manipulation of digital handwritten text. And in another example, we see the sketch RNN architecture. It's one of the pioneering work in this field. So here, the authors propose a sequence architecture where the encoder and the decoders are LSTMs, and the latent space is regularized by VAE objective. So you feed, again, like instead of handwritten text, this time we feed a sequence of points for drawings, such as basic shapes, objects, animals, and then we decode it. So since we have a VAE latent space, it allows us to generate novel samples as well. And this representation, the point-wise representation and this RNN-based architectures worked quite well in these problems. So instead of going for the point-wise representation, we propose a novel approach. So we treat the ink data as an unordered collection of strokes. So what's a stroke? Let me define it. So here in this example, every color corresponds to a stroke. It's basically what we draw until we lift the pen up. So the stroke representation is in fact a very, very strong prior, because like it is how we segment a full drawing or handwritten text into its atomic units, like mentally and physically. It's what we can draw comfortably, because we don't draw something as a whole, right? We always divide it into pieces. So it also comes for free. So what we do here is that we just use the pen labels, and like if it's one, we just divide the entire sequence from those. And now we have like segments. So strokes can be meaningful instances, like such as the full circular shape here, or like diamonds or arrows, or it can be something arbitrary as well. For example, here, like now, like it's constructed by using a lot of strokes, right? And by the way, this is one of the still good samples we had in the data set. So there were really terrible ones. So it's the natural representation for humans, and we just decided to use actually like what has been in front of us. So our focus lies on generative modeling of such stroke-based data, and like I can define our task as like to predict where and what to draw next given a partial drawing. And in this problem, multimodality is our main issue, main challenge. So in handwriting, localization of the next stroke is rather easy, and it's often determined by the previous stroke, previous characters, right? Because we follow a writing order. But if you look at the sketches, it depends on the semantic category, and the order of strokes can be determined by the user. Like every user can draw something in a very different order, but eventually the models learn like what a cat or elephant sketch look like, and like it's still more like less straight. It's still straightforward for the model to make a prediction. But if you look at a diagram drawing, and especially if we don't know about the context, in other words, if we don't know what we are drawing the diagram flowchart for, then the next stroke is not tied to any global semantics, right? So if I tell you, look at this and draw another stroke, put another shape, like you can select any arbitrary point and you can put any arbitrary shape. So this actually implies combinatorial complexity. So we took the sketch-on architecture, which was designed for basic shapes, right? And we trained it on this data and evaluated by increasing the number of strokes. As you can see in the beginning, it was fine, but it cannot cope with the increasing complexity. And it's mainly because it treats the data as a sequence of points. So instead, we consider the compositional structure of the data and model the ink data as a collection of strokes. So, and this enables, like this allows us to achieve better results and design a better model. So, like treating the data as a collection of stroke is one of our core contributions. But when you just switch to another data representation, of course, you have to design another model. Now we can no longer simply pass the data into an RNN-based architecture. So after an overview and motivation part, so let's continue with the modeling. So I'd like to talk about our inference pipeline, which should give you an overall idea about how our architecture works. So here you see an example sketch consisting of 3 strokes only, S1, S2, and S3. So we represent a stroke with itself and its starting position denoted by the bar symbol. And we subtract the starting positions from the strokes and translate everything to the origin. So in other words, every stroke is assumed to be starting at 0, 0 coordinates. And as I said, our task was to predict where and what to draw next. And we define it as an auto-regressive problem. And we factorize the joint distribution over the entire drawing X as a product of conditional over the available strokes and their starting positions. And in this example, for example, K equals 4, and we are trying to identify S4 by looking at all the available strokes. So as I said, we subtract the starting positions and translate everything to origin. So this decomposes the drawing actually into strokes. and we no longer keep the global information in the first phase. And in the first phase, our goal is actually projecting these variable length strokes. Each stroke may have arbitrary length, arbitrary number of points. We want to project them into a fixed dimensional representation space. Here, like different encoder architectures just represent the idea, the independence assumption. So like it assumes that like the encoder doesn't see any information about the entire drawing, but it just gets every stroke independently. So here, what we want to do is to capture only the local information about the strokes, so such as the shape, size, or curvature. So we don't intend to learn anything globally, like how they relate to each other. And now, after this encoding step, our canvas, our drawing is represented with the strokes embeddings and their corresponding starting positions. So it's kind of like a drawing in a neural representation space. So in the next phase, we use a relational model. Now it's time to model the global semantics, the dependencies between the strokes, like such as the layout, or like how they position with respect to each other on a canvas, like how, for example, different types of shapes or entities relate to each other. So here we use a relational model. It means that like it does like pairwise comparisons and relate strokes with each other and learns and extracts the representation internally. And then by looking at this representation, we make a prediction for the next strokes embedding. It's still, the prediction is still in embedding space. And then we make a prediction for the starting position for the next stroke. And after this operation, now this is the final stage of our canvas. So now we have our prediction as well. Actually, like learning the global semantics and learning how to compose strokes into more complex drawings as here, only in the abstract representation space is our second major contribution. So this relational model does not see anything about the actual drawing. It just looks at the abstract representations and the starting positions and then makes a prediction. So this is something important. And in the final stage, like now we have to return back to the original input space for the users. So we get the prediction and we pass it to our decoder, which I'll give you, like, which I'll explain in details in a minute. And then finally, we render this stroke back and we visualize it for the user. So in this case, for a given initial partial sketch consisting of S1, S2, and S3, now our model completes it with the prediction of S4. So this is the overall picture, like how the inference looks like. So we start with a partial sketch. We encode, like we project every stroke into like onto a fixed dimensional representation space. And then we pass this information to our relational model, which gives us a prediction, makes a prediction for the next strokes embedding and starting positions. And we finally decode it to achieve our final result for the users. So let's look at the details of the models. Here you see this stroke autoencoder architecture. In the inference pipeline, this was split into the encoder and decoder parts, where we had the relational model in between. But it's actually itself a whole component. So as I said earlier, our task was projecting the variable length sequences into a fixed dimensional embedding space and then reconstructing them back, right? So we could simply use a sequence architecture, such as the sketcher and N model. In fact, it was one of our earlier models as a baseline, and like it didn't perform well because our task our task requires high quality representations. So the embeddings must be like good enough, informative enough for the reconstruction, so that we can like project them into neural space and then reconstruct them for the user, render them. And they must also be informative or structured enough so that our relational model can make the predictions, because the relational model learns the globals, like global semantics in the representation space. So since okay, in the encoder, we still treat these strokes as a sequence of points, like similar to RNNs. So instead of using an RNN architecture, we just use a sequence transformer. It performed marginally better. So it just similar to RNNs, it looks at the stroke data point by point as in the drawing order. So this part is easy. And then it outputs a fixed dimensional representation lambda. So, but in the decoder, we abandoned this sequential approach and we propose a novel decoder architecture, which considers a stroke as a curve in the differential geometry sense. So a 1D manifold embedded in 2D space. So we assume that there exists a differentiable map S, right? Here is the function, and it's parameterized by a scalar value t, and it gets this t value and gives us the coordinates, the corresponding coordinates. So it means that if the t gets the value of 0, then it corresponds to the first point of our stroke, so which is here. And if we pass 1, then it corresponds to the last point in our stroke. And when we implement this, we augment this function by using the stroke embedding, where the decoder gets all the information about the stroke. And then it parameterizes it by using the t values. And here, like, we can pass any like stroke embedding and then t pair, and then we can get the corresponding point on the screen. So this has the advantage of being parallel. So we can run it in parallel, like similar to passing an entire batch, and we can render this stroke in one go. We don't need to wait for prediction of the previous one and then feed it and then get the next one. So this was the main advantage here. This is crucial because when you run such a big algorithm, like on a hardware, on a tablet, on a device, like you cannot you cannot have very high latency. It should be fast. And since we no longer since we no longer treat them as a sequence in the decoder, we just stack 4 dense layers with a relative activation, and it's as simple as it is. And our decoder has also a very nice side effect. So it allows us to control the output resolution. So in other words, we can control the sampling frequency. And here you see 2 examples, like 2 stroke examples. So in the first line, we have an arrow. In the second line, we have a circular shape. So in both cases, like, we use the same stroke embeddings for all the instances here, and we just change the number of t points. So here, for example, we use just 5 points. So we sampled the interval 0 and 1 5 times uniformly and passed them to decoder, and this is what we get. So as you can see, okay, we lost some of the fine-grained details, but the overall stroke shape is still there. So it's actually a very good indication that our stroke embedding, our representation, is able to capture the local details. So it spans all its capacity on the local information. And as we increase the number of sampled points, as you can see, we gain like the fine-grained details. And like after this point, there is no perceptual difference, but it implies that we can decode, we can render a stroke in infinite resolution. Sorry. So during training time, even if the model like hasn't seen like all the potential pairs of T and stroke embedding, it learns to generalize to this concept. Okay, get the information from the embedding and then give me the corresponding point on the screen. So it really learns the 2D function, like per function that we assumed for. So, okay, let's look at the relational model. I showed you a 1 block in the overall sketch, but instead we factorize the task into the prediction of the starting position of the next stroke, and given that the embedding of the stroke. So this helps the model to better learn the influence of the starting position on the predicted strokes, and I'll show you an example very soon. Here, since like in the beginning we made a like set assumption, we assume that the drawing, like any drawing on handwriting, can be treated as a set, right? Here we use a set transformer. So this gives us this gives us permutation invariance property. So it means that if you swap the order of the strokes or entries in your data, it doesn't matter, the output will be the same. So this is actually a very, very good property, and it was something we needed because, as I said in the beginning, especially in the case of flowchart modeling, it was like the complexity is combinatorial. So here, once we gain the permutation invariance, like we saved a lot of modeling capacity. And in addition, additionally, we use Gaussian mixture model outputs here, again, to better deal with the multimodality, because on a 2D canvas, right, if you look at here, so like the next stroke can be anywhere arbitrarily, right? So there's no, it's not deterministic, like there's no single point we can start drawing. So different users make different assumptions. That's why we modeled it by using a Gaussian mixture model. And similarly here, like to be able to predict multiple stroke types, we again use a Gaussian mixture model. And here we see how it looks like. So in these two examples, the black ones, the black strokes are given to the model as context. So then the model predicts the stroke position, which are, for example, here highlighted with the red heat map. So like, for example, for this case, the model tells us, okay, I can start driving from here or this position. And if we sample this starting position, then the model in the next step, here in the next step, the model predicts a circular stroke. But if we go with this selection, with this starting position, then it draws a square. And in the second example, like the points, the starting potential, like the potential starting candidates are a bit distinct. But in both cases, like if we select this one or this one, it doesn't matter, because for the model makes a prediction for an arrow, which is feasible in this scenario. And here we see what happens. Or here actually we are looking at like the other alternatives, other candidates of the stroke embedding prediction model. So given the same, like given the starting positions denoted by these positions. So here the models tells us that the first three top candidates can be these, so which are like different shapes, different entities in this example. Here they're all arrows, but in different shapes and like looking at or pointing at different directions. And the blue one is always the top candidate, the most likely one in the GMM space. So here what we see is the auto-regressive predictions of our model. So every column corresponds to one step. So again, the black ones, they're always given to the model, and the model makes a prediction for the red, like as a starting position here, like this is the GMM distribution. And when we sample a point from here, and then this is the stroke prediction it makes. Of course, here what you see is the rendering result from the decoder. And if we like skip some intermediate steps and look at this case, so this is the prediction. And at every step, we predict something, we decode it, and then we put it in our like context, like in our input set, and we pass it again to the model. So it's auto-regressive. The model sees its own predictions as input. And as we grow, like as we continue, like this is how it evolves. And at the bottom, you see a lovely cat example. And again, the black ones is given. So like, actually it was an interesting sample because like once, for example, there's an eye, the model learns to put the other eye. So it learns the symmetry actually in this as a cat-like shapes. And then once it's there, like it completes the face. And if we still ask for another stroke to the model, then the model starts drawing the whiskers, right? It starts here. As you can see, it could also start here, but since we sample from the starting position distribution, we start from here, and then like it continue, and then it completes the cat example. And here I'd like to share just more results from the model. So it's not just limited to, let's say, more like structured flowcharts or cats. So for example, this is an example like on the right-hand side, like elephant shapes, or like as a proof of concept, we also train our model on handwritten text. So of course it's unconditional, so the text shouldn't make any sense. But when we asked the model to just like write something, like these were the letters, at least it was able to understand the structure of text and the letters. So after some qualitative samples, I'd like to briefly mention the quantitative analysis and show like how quantitative analysis validates our design choices. So in the quantitative analysis part, we use the chamfer distance. The chamfer distance basically measures the discrepancy between 2 point clouds, S1 and S2. So for a point X in the point cloud S1, what it does, like it finds and it identifies the closest point in the point cloud S2, and then it reports the error. So this is how it works, and it's bidirectional, so it does the same operation for the second point cloud. So we basically after we decode our stroke by using the decoder, we compare it with the ground truth one by using this. And for the prediction cases, since the task is highly multimodal, we proposed a stochastic variant. And since we have Gaussian mixture predictions already, we are able to predict or like make multiple predictions, multiple samples from our model. So for example, we make 10 samples, we get 10 samples from the model, and then we report the one that has the minimum distance, right? Because the most likely one, for example, like the ground truth can be, let's say, a circle, but the most likely model prediction can be a square, but the second most likely one can be a circle again. So just to be able to deal with this multimodality, we use this stochastic variant. So we have two metrics for the reconstruction performance, which evaluates the autoencoder, so which is in this column only. And then we have the prediction metric, which evaluates the relational model and the decoding performance. So I just would like to highlight two cases. In the first one, what we see is that like we built the model by using our relational model and basically following the set-based assumption. But as an autoencoder, we use the sequence-to-sequence baseline instead of our autoencoder. So the sequence-to-sequence baseline is basically an RNN, an LSTM as encoder, and another LSTM is the decoder. So it's basically, it's a different architecture, different concept than ours. Sorry. And if you look at the reconstruction performance, actually the performances are very, very similar. So here what we do, we get a stroke, like ground truth stroke from the data set, pass it, get the embedding representation and decode it, and we compare the reconstructed stroke with the ground truth with the input. As you can see, they're really, really similar, like almost no difference. But if we look at the prediction performance, we see that when we use our stroke autoencoder, the prediction performance is significantly better compared to a sequence-to-sequence autoencoder. Actually, this is what I tried to say earlier. So the embeddings must be informative both for the reconstruction task and the prediction task. And our decoder actually allowed us to, like our decoder helped us to achieve this. In the second instance, what we do is that we use the same stroke autoencoder, basically our architecture, and replace the relational part with an RNN architecture. So we abandoned the assumption, and and we basically feed the stroke embeddings like in an order by following the drawing order actually. And here, like we see again a significant difference in the prediction performance. Even if we use the informative embeddings from our stroke autoencoder, if we abandon the set-based architecture and follow a sequential RNN-based architecture, we lose, actually the performance degrades significantly. So like these two evaluations validates our design choices. And finally, here you see the application demo. As I said earlier, we model time series so that we can directly interface our model with an application. And like here, our model runs on this device. So it does not connect to a server, for example. So it's local in this device, and it allows interaction and collaboration with the users. So to conclude, I'd like to sum up the first part of my talk. So we treated the digital link data as a collection of strokes, and we followed the compositional approach. Decoupling the local appearance from the global semantics was another crucial design choice. And we proposed a novel autoencoder to learn informative and structured representation space for the strokes. And we finally like use a relational model to learn how to compose individual strokes into more complex drawings only in the abstract representation space. And we also have a project page. If you would like to see more results, more details, you can visit it. So this concludes the first part of my talk. I'd like to continue with the second one. In this part, I'll briefly mention you about our other work on representation learning for 3D human motion prediction. Although the problem is very different and it's not exactly the same concept with the digital ink model, but we still follow a similar approach, so decompositionality. So let me briefly introduce you the problem. So here we are modeling 3D mockup data. So it's basically a sequence of 3D poses, as you can see here, like skeletons. And our task is, given a CD motion, for example, like 2 seconds into the past, we would like to predict the future. So it can be like 1 second in short-term prediction, or like much longer in longer term. And we would like to make, let's say, accurate short-term predictions and plausible long-term predictions. Because as we keep making predictions by feeding our predictions back, right? So we make a prediction, we feed it back, and we predict the next one auto-regressively. So this starts deviating from the ground truth. So long-term predictions are no longer accurate. They cannot be accurate. It's expected to be diverse. And our expectation is to have like something feasible. And we have the skeletal information in this problem. So we know how the skeleton is constructed. We have K joints at time step T, and we represent the data by using joint representations in 3D. So it can be 3x3 rotation matrix, quaternions, or like even directed 3D positions, X, Y, Z Cartesian coordinates. So when we look at the literature, the previous work, it's common to flatten all the joints to get a pose vector. So this means that we just dump all the data in a single vector and then represent the motion data as a sequence of pose vectors. And this is usually modeled by using temporal architectures. And in the more recent related work, like people started abandoning this idea and like started considering trajectories of every dimension in the pose vector. So for example, if we have X, Y, Z coordinates for my hand, right? Then like I consider the entire trajectory, the given sequence of the given sequence for the Z coordinate of my hand joint. And when I do it for every coordinate. So model it or treat it as trajectories. So in the first approach, I call it explicit because it explicitly models the temporal information. So we usually follow an auto-regressive approach by using RNN-like architectures or like temporal CNNs, convolutions. So what we do, we take the given seed motion, like what we have in the past, and we summarize it by using the architecture. For example, we get the context by using RNN's internal state, right? RNN's internal hidden state H. And then given the previous step, we make a prediction for the next one. And we pass our prediction back to the model and we auto-regressively make a prediction into the future. So we unroll it. So the problem here is that the model has to maintain long-term temporal relations, right? Because all of the information, like temporal information, is summarized into our internal hidden state in this context vector, so which may not be very, very accurate and representative. And secondly, since we use the pose vectors, so everything is flattened, right? We no longer keep the skeletal information. The dependencies between the strokes have to be modeled implicitly. So the model has to expand some of the modeling capacity to learn about the skeletal structure. In the second approach, like I call it implicit, where people use the trajectories. So I call it implicit because we no longer model the temporal data directly. Instead, as I said earlier, so we get the trajectory of a particular dimension, we pass it to a transformation function, such as discrete cosine transformation, and we now have the coefficients, like DCT coefficients, representing that trajectory. And then a graph convolutional network tries to learn the skeletal structure. So it makes the predictions, again, for the future in the DCT domain, DCT frequency domain. So, and then we run the inverse DCT to get the trajectories into the future. So this is how it works. And as I said, it's implicit because it doesn't look at every step explicitly, but it looks at the entire sequence. Like it takes the entire sequence and makes the predictions in one go. So in this approach, we argue that actually the temporal modeling is limited by DCT's representative power. So, and instead, like similar to our previous work, so we start decomposing the given data into the atomic units again, And in this case, the atomic units are joints, right? The joint rotations, it's what we have. So rather than going every individual dimension, we treat every joint as an atomic instance. So it's again, not the most fine-grained representation, but something intermediate. It's also not as coarse-grained as the entire pose-wave. So we decompose it into joints, right? Here, like every circular entity corresponds to one joint, and we project them again into a representation space. And we do this for the entire motion sequence. So now, like, we have it decomposed, and for a particular joint, here it's the shoulder, we first run a temporal attention. So what it does, for that particular joint, it looks at the entire history of that joint and identifies the most informative instances in the past. So, okay, how did my shoulder move in the past? So this can be interpreted in this way. And in the second step, we run a spatial attention. And what it does, basically, it just looks at the other joints in skeleton. So to identify the most informative joints in the others in the skeleton at this time step. So we are no longer interested in the past for the other joints. Then we fuse this information to update the joints representation, and we do this for all the joints in parallel. And here actually this allows us to learn joint-wise representations. So the joints, or like every joint, has the freedom to learn a representation, like the most informative representation for its own, because later we use these representations to make the next steps prediction. Here we still follow the auto-regressive approach, right? So this is how we learn the representation, and then we pass the joints representation to some output layer, which is like a few dense layers again, and it predicts the joints rotation in the next step, or joints 3D position in the next step. And then we construct our pose and we give it back. So in order to learn better representations, we stack a number of these layers, and it works in a message passing fashion, because once the joint is updated, right, in the next step, the same joint now gets updated representations from the other joints. So in this way, our model learns better representations, as well as it learns how to compose the joint-wise representations to generate temporally coherent pose. Okay, here I like to show you some qualitative comparisons. So on the left, you see an RNN-based architecture, and then what we see here, the DCT-based architecture. As you can see on the top, for a simple walking motion, since like all models work auto-regressively, so we get the predictions and feed it back, right? So the RNN-based architecture stopped already, but like this one like did well until this point, and then it was like our model was the best. I'd like to run this again. Yeah, so this architecture was still okay for the walking-like motion, but it's not stable as our model. And in the lower, what we see is slightly more complicated case, and like both of the models stopped immediately. It means that like it cannot handle the auto-regressive prediction cycle, but our model was able to recover at least the sidestepping motion. And since it's a, let's say, periodic motion, it's able to continue doing this. And here you see the like more results from our model, just rendered by using the mesh. So we always predict the internal like skeleton inside, and then like we can also visualize them by using meshes. So this concludes the second part of my talk. To conclude, today I presented two of our recent works on generative modeling of ink data and 3D human motion data. In both works, we design models that learn representations for the atomic units that we define, and how to compose them to generate realistic samples. So this approach, like compositionality, makes the models robust to increasing complexity and the noise observed in the auto-regressive prediction cycle. As the model's predictions are not as accurate as the ground truth ones, like eventually the error accumulates in time and the models start diverging. And we saw that, like I showed that, once we like empowered, once we embrace the compositional and structural priors in the task, in the data, like the models becomes more robust. So I'd like to thank you all for your attention, and I would be happy to answer your questions.
Thank you, Emre. That was a really nice presentation.
Thank you.
It was really colorful in the literal sense and in the abstract sense. Any questions from the audience?
Maybe I can ask.
Yeah, sure. Yep.
So very nice talk. I followed it with great interest.
Thank you.
We've been also looking into various attention formulations in, let's say, different domains, not action modeling per se, and different problems. Sorry, I don't see my camera. I don't know how it looks. But I'm curious about one thing. Sometimes we realize that attention modules yield great results, but not always really learning the attention, but learning, sometimes learns degenerate attention mechanisms, but still yields good results because they are kind of nonlinear structures. So I haven't had the chance to look into the paper, but I will. But still asking, like, have you looked in what kind of attentions do you learn? Does the model, yield? And have you explored things like sharing, not sharing parameters across these attention module layers? Modules, not layers, but across the modules, and how it affects when you change the number of modules that you have. I'm curious about your experiences in these technical details.
Okay. Yeah, I understand the question, and I totally agree, because like sometimes, we visualize the attentions, of course, and sometimes they are not as intuitive as we expected, right? Maybe I have a result here. Can you see my screen? Yeah. Okay. Yeah, here, actually, this is a great example. What you see here is the attention visualization, right? So the red one is the prediction, and then it's the attention highlighted in blue. And what we like, let me rerun it. So I was expecting, to be honest, like more diverse attention, but what we realized is that it mostly focuses on the most recent one. So the model makes a prediction, but while making the prediction, the highly attended stroke is usually the most recent one. So for example, it doesn't jump from here to here, like for let's say more global information, but somehow it still handles the complexity. It can like keep making predictions. So I think this is what you meant. Yeah, I was expecting to see more diverse, like more meaningful patterns, but yeah, this is what we end up for.
And especially I was asking for the second study. So I'm curious about what kind of attentions do you see, and how, it affects if you share parameters, let's say, across the modules that you have, or if you don't.
So like, first of all, for every joint, we used a different layer, right? We didn't share the information between the joints, or we didn't share the weights. And if we share them, the performance degraded significantly. So this was the first problem. And second, when we visualize the attentions, like only at the first layer, we had like representative, meaningful, intuitive attentions. After the first layer, once we keep stacking, like it was almost like very uniform. But this wasn't also very intuitive in the second part. I had some results.
So that's exactly my experience. Very quickly, it degenerates and turns into things that are almost like average pooling.
Exactly, yeah. For the motion case, for the motion scenario, in both the temporal and spatial blocks, this was the issue we observed. In the first block, yes, it was fine. So the model was attending some of the joints, actually particularly like, let's say, not the end effectors, because they were moving really fast. So we felt like the model was trying to seek some reference points, right? Like such as the root joint or like shoulder joints, like which are not moving actively, like barely moving. So they were like mostly attended ones. And for example, for the right hand, like naturally was mostly attending on, let's say, the left leg. I don't know why the leg was attending the leg. But this phenomenon was only observed in the first layer. Once we look at the like second layer or even the top layer, we saw almost like average polling, like very similar attention weights. And to be honest, I don't know why this is happening.
I think, you know, the model cheats in a way.
Probably. The other factor could also be that like this attention-based architectures were originally designed for language data, right? The data is tokenized, so we have tokens. But here we are running them on just real valued data. So like this is also what I think. Like there is no really like a clear attention concept, because now it's in a real valued like representation space, and like yeah, if you just take an average, it should still be fine, probably. Like, and we haven't tried it on any tokenized data in case of motion.
And in your case, what I couldn't fully understand is whether the, let's say, second layer attention, does it go back to the original data, or does it look into the outputs of the first attention module?
Outputs of the first one. Outputs of the first one. So it's really like a message passing update, and they keep refining it.
And the trainable parameters, are they shared across these modules?
No.
Okay.
Like they're all different. Like across the joints, across the layers, we always use different ones. And yeah, we tried, of course, sharing them, and we wanted to check like how it changes the performance, like using separate weights across the joints, across the layers, like were the best in the end. And in fact, like if we could fit, let's say, a larger model, the performance was getting better and better. So I don't know. It's really like, yeah, you need to use bigger models when you use attention, probably.
Okay. And it's really like graph neural network layers, but not the origin, because you have this at norm that construct that comes from transformer.
Yeah.
So it differs in that end, but probably much more stronger. So very exciting. Thank you very much.
Thank you. Yeah, I agree that it's very similar to graph neural networks.
There are also papers saying that like attention graph, they are like hand to hand, not exact finally, you know, there are many small differences.
Yeah, in the design choices, we can see differences, but the concept is very similar.
Yes.
Very equivalent.
Sorry?
They are said equivalent in terms of
certain. If you simplify attention formulation, and if you choose the right graph neural network formulation, I think they end up being equivalent.
Yeah.
But I feel that attention point of view gives you more flexibility, because you can be more, you know, trying to make things right in the GNN formulation can be restrictive in some ways.
Yeah. Okay, any other questions, comments? I have some questions. So regarding the first part, so the final results that you have shown, like drawing, text, prediction, etc., were they from a single model, or
no, different models for different tasks? Yeah. Actually, it was the goal, like one model ruling all of them, right?
Yeah.
Yeah, the model. Yeah, actually, we didn't have much time for data cleaning, data preparation, and of course, like scaling of handwritten text or like drawings, they were very different. And we realized that the model actually struggles a bit when we pass all the data during training. So yeah.
Okay. I see.
But with a bit of pre-processing, like good pre-processing, like data scaling, it should also be possible, probably.
Yeah, I think so as well. Did you try to visualize the embedding space? So how does it look like?
Yes, we visualized. Actually, the first project like took a year So like until we got really good results, and like we tried many things. And yeah, visualizing embedding space was part of the analysis. We see something structured, right? Like for example, arrow like strokes, like they are in some, like at some point, and like you see like other clusters corresponding to other shapes. But yeah, it wasn't really like meaningful in the end.
And regarding the last model, so in the attention part, you're attending to the outputs of the other joints. So what if I want to, for example, attend to the position of another joint, let's say 10 seconds ago? So we are missing in terms of that flexibility, right? Did you try that, or?
Yes, we tried it. So we didn't do it explicitly because it introduces a lot of computational overhead, right? So this also limits the modeling capacity. As I said earlier, if you can increase the dimensions of the representations in the transformer, like we got better and better results. But first of all, when we implemented what you just suggested, like we couldn't fit the same model, so we had to lower the number of parameters. So this hurt the performance. And second, in our approach, that's why actually we stack a number of layers, right? So yes, in the first step, we cannot get any information about any joints past instance. But once we go to the second layer, now that joint, the other joint, is updated, right? So it gets information from its own past instances, and this, like indirectly, this information is retrieved by our point of interest. So that's why we stack multiple of them.
Okay, makes sense. Okay, maybe we can stop recording, then go informally. Thank you, Emre, again.
Yeah, thanks for inviting me.
We will continue informally now.